Hey everyone, this is Saritesh Tiwari, member of COPS IITBHU. Today I'll be discussing Problem D, Social Network of Codeforces Deltix round Autumn 2021. Just a disclaimer that my solution requires a prerequisite of disjoint set union. Now coming to the problem statement, the problem says that William has arrived at a conference and it has n participants numbered from 1 to n who are initially unfamiliar with each other. William can introduce any two people, A and B, who were not familiar before, to each other. Now, we can visualize this as a graph problem where people can be seen as vertices and introduction can be seen as an edge, right? So when A and B are introduced, we can have an edge between them. Now, William has D conditions, ith of which requires person xi to have a connection to person yi. Now, when are two people connected? So xi can have a connection to yi when either it is directly introduced or xi is first introduced to a person yi, then xi is first introduced to a person p1, then p1 is introduced to p2, then p2 to p3, and so on and so forth up to pk, and then pk is finally introduced to yi. So this is in this condition also xi and yi are said to have a connection. So the dith condition boils down to have xi and yi in the same connected component. Now for every I belongs to 1 from D, like William wants you to calculate the maximal number of acquaintances one person can have, assuming that William satisfied all conditions from 1 and up to I and performed exactly I introductions, right? So acquaintances are immediate neighbors. So in this graph you can see vertex A has 3 acquaintances, vertex B has 1 acquaintance as it is only connected to 1, then vertex C has 2 acquaintances, and vertex D has 1 acquaintance, and vertex E has also 1 acquaintance, C. So William asks us to calculate the maximum number of acquaintances for every I from 1 to D. Alright, so now let us come to the first test case of the problem. I will be using a whiteboard. So the first test case says that we have n equal to 7 people in the party or vertices and d equal to 6 conditions. So the first query says that 1 and 2 must have a connection. So this is the only possibility and the answer in this case would be 1. Then the second query says that 3 and 4 are also must have a connection. So 3 and 4 also must have a connection. In this case also answer equals 1 as the maximum number of acquaintances is 1 for any vertex, right? Now we come to the third query. The third query says 2 and 4 also must have a connection. So the one approach can be to connect to directly introduce 2 to 4 and have an edge between them. In this case, the answer would come out to be 2. But we don't necessarily have to take this as our starting point before the third query. So we can build an entirely different graph from this instead of this graph. So like let's suppose I make this graph like 1 is connected to 3, then 1 is introduced to 3, then 1 is introduced to 4. Like this also satisfies the first three conditions, sorry. 1 has a connection to 2, 3 and 4 have a connection, and 2 and 4 also have a connection, and it also has just 3 introductions, and the answer in this case would be 3 as opposed to 2 in this case. So this is a more optimized approach. So this basically boils down to when two vertices of different sets have to be combined together, then the answer would be size of component 1 plus size of component 2 minus 1, right? As we can see in this case where like 1 and 2 were connected at first, so like 1 and 2 were only connected and 3 and 4 were connected, right? So this has size 2, 1 and 2, and 3 and 4 also has size 2. Then we took 2 and 4 to have a connection between each other which belong to different sets. So the answer could have been calculated like answer equal to 2 plus 2 minus 1, right? And we would get 3, which is the correct answer. Now we look at another test case, which I have formed an easy test case, which says uh, n equal to 7 and d equal to 4. So 4 conditions are there and 7 vertices are there. So let's first make all the vertices in this test case. So 3, so there are 7 vertices, right? So this is the basic implementation. So firstly it says 1 and 2 are connected. So answer in not for the first query would become 1, right? Because the maximum number of acquaintances is 1. Then it says 2 and 3 are also connected. So we can connect 2 and 3 and the answer would become 2, as 2 has 2 acquaintances. Then it says 1 and 3 are also connected. Now you see 1 and 3 already had a connection because 1 was connected to 2 and 2 to 3. So we take x, let's suppose x, let x equal to number of extra edges. We will say 1 comma 3 is an extra edge, right? And we will take this as 1 because we will count 1 comma 3. Then like this extra edge, now this is an interesting like point of this problem. Like when we have an extra edge, we can connect like instead of connecting 1 to 3, we can just connect like 2 to 4, right? We can utilize this extra edge anywhere and we can increase our answer. First the answer was 2, now our answer is 3 for the third query, right? Okay, but we won't make this edge, we will just count the number of extra edges till now. Then we come to the for the third query we will print answer equal to 3, and then we will come to like the next query which says 5 and 6 are also connected, right? So 5 and 6 are also connected. This connected component has a size of 2, this connected component has a size of 3, right? And now we have an extra edge. So then that extra edge can be utilized to connect these two connected components with each other, as like we can have that extra edge from 2 to 5, and instead of 5 to 6 we can connect 2 to 6, and then our answer would come out to be 1 2 3 4 4 for this query, which is I think the maximum answer we can get, right? So what extra edges does is like basically tells us how many number of connected components should we take into consideration, right? So now what my approach for this question was to get the size of all connected components at a particular for every I, like we get the size of all connected components in an array V, and then let me show you the pseudo code for this problem. So let x equal to 0 be the number of extra edges before like I have taken input of any like condition. Then for every condition I input u comma v. Then I check if u comma v belong to the same set. If they do belong to the same set, I increase x by 1. Else I merge the sets of u and v. Then I build a vector v with sizes of all connected components, right? So in this case, for example, in this case, it would have 3, 2, and 1, right, for the last query. Then I sort v, and my answer for this query would be sum of size of largest x plus 1 connected components minus 1. Now this is the understanding part of the problem, and now let's come to the coding part. So this is my code. So I have basically used a structure for disjoint set union DSU, named DSU. Then let's come to the main part. I have coded in C++. I input n and d, then I declare a disjoint set union of size n. I initialize x as 0, extra edges is x. Then for every query I input u and v, then check if they belong to the same connected component. If they do belong, then I increase x by 1, else I merge those two connected components. Then I have a Boolean vector of size n plus 1 and I initialize it with false. And I have a vector v which is empty. In this I will store the size of the connected components, right? Then I iterate from every node from 1 to n and check if its parent is visited. We can find the parent of it using disjoint set union. And if it is not visited, I push in the array the size of that connected component and I put visited of the parent equal to true. Then I sort all of the array in increasing order. Then like I introduce int cnt equal to 1 plus x and int answer as 0. Then I take the last 1 plus x, like 1 plus x elements of the vector v which was already sorted, and then I output answer minus 1. That's it for this video. If you enjoyed the video, do give it a thumbs up and do comment and share. Thank you.